In this video, I'll teach you how to solve problems with Newton's laws and free body diagrams. So before we start, I have to explain to you what a free body diagram is. A free body diagram is a diagram of a single object and all the forces acting on it in isolation. This helps you analyze whatever's going on in a problem, and it's usually the first step you take to solving a problem with Newton's laws involved. So up here in the corner, I've wrote a little problem solving guideline, which I'll show you how to use in this example. Imagine you're studying with your friend and you're in the library sitting at a table. We're going to ignore friction for this problem. Now you have a book and this book weighs 10 kilos, right? Let's write that down, 10 kilos. Your friend wants to borrow the book, so he pulls it by the attached string in this direction with a force of 40 newtons. The angle at which he pulls it at is 30 degrees. What is the acceleration of the book as it slides along this table? Let's use this problem solving guideline. So step 1 is to sketch things, which we've done. We understand the problem and what's going on. Step 2 is to draw a free body diagram. It's very simple. Let me walk you through it. We're just going to use this because this works pretty well. Let's think about all the forces acting on this book. So of course we've got this 40 newtons, which we're going to label FP. P for pull, right? There's also the force of gravity acting on this book. And because there's gravity, there's also the normal force, just going this way. There's our forces. Now how do we find the acceleration? Step 3. Resolve the force vectors into their x and y components. Now our coordinate system, our chosen reference frame, would be y going up and x going to the right. The acceleration of the book as it slides along the table would be in the positive x direction. That means we can disregard these vertical forces entirely because they don't affect the horizontal motion. Then what is the horizontal motion? Well, it's the horizontal x component of this vector here, which we can solve for with the formula fpx, so the x component of fp is equal to the magnitude of the force, which is 40 newtons, multiplied by cosine 30 degrees. We take 30 degrees from here. Put this into a calculator, you get 34.6 newtons. Great, now we know the force in this direction. Time to find acceleration. And we do that with step 4 in this problem solving guideline. Apply the second law. Newton's second law is F equals ma. If we divide both sides by m, we can find acceleration, which is a equals F over m. That's great, let's plug in our values. So F being force is 34.6 and mass, as we know, is 10 kilos. That means the acceleration of the book as it slides along the table is equal to 3.46 meters per second squared. Now, what if instead of trying to find acceleration, you try to find the magnitude of the normal force being exerted on this book? So the normal force, let's solve for that. Well, okay, let's use this problem solving thing again. We've got the diagram, we sketched it up. We just have to resolve the vectors now. So the pull vector in the upwards y direction, we can find it similarly to the x component, which would be 40 sine 30. This is equal to 20 newtons. So 20 newtons upwards. Now we're ready to find the normal force. Let's apply the second law to all the y components. The sum of all y components is equal to ma. Now, what's the net y force? It would be Fn, because that's going up, so Fn plus 20 newtons. And then mg, gravity, is pulling it down, so we'll take away gravity. And this is equal to ma. Now, mg is actually 10 times 9.8, which is mass times gravity. Let me teach you about tension in flexible strings and chords. When you have a chord and this chord's mass is very, very small, it's very light, you can just consider it as zero. It's negligible. So when under tension, when something's pulling on it from both sides, then the net force on both sides would be zero. And here's why. When you look at net force equals MA, the mass is zero, right? We're just pretending it's zero because it's so light that it's not even worth considering the weight. That means M is equal to zero, which means that the total net forces on this string when under tension is just zero. The reason why I explained this to you is because in the next example, we're going to be dealing with strings and chords. Here's the example. So you have two tubs of ice cream, and these two tubs are connected by a cord. The second tub has an extra piece of string hanging off the edge. We're going to label these tubs. This is tub B, this is tub A. Tub B is 6 kilos and tub A is 5 kilos. If we pull on this string here with a force of 40 newtons, what is the acceleration of these two tubs? Now I quickly made our sketch smaller because the next step, as you can see, is to draw our free body diagrams. It's recommended that you draw one diagram for each object because then you can look at the forces acting on these objects individually. So let's draw a diagram for ice cream tub A. Remember, you should use simple shapes in these diagrams because it just makes it way easier. You don't have to make an intricate drawing. Let's think about the forces acting on this box. So let's choose the most obvious ones first. Obviously, we got the pull here, so FP. We also have gravity, because gravity is always there. Gravity is mg, but we're going to label it as mag to show the mass of A, which is 5 kilos. There's also the normal force counteracting this gravity, which we'll call FAN. Again, A means box A. And there's one last thing. There's also the force going this way, which is the tension on the rope connecting A to B. We're going to call this force FT, T for tension. Now this labeling process, I've been pretty specific, but it's really up to you how you want to do it. Different textbooks and different teachers will teach you different notation. Just so choose the style that just makes sense in your brain. The notation I use, this kind with the smaller letter in front of the big letter, it's pretty common. So if you want to use this, go ahead. Anyway, moving on. Step 3, resolving the vectors. So if you remember, we're looking for the acceleration to the right as we pull this box. So let's resolve all the vectors into the horizontal components. These two, gravity and the normal force, they have none because they're going straight up and down. For F pull, the horizontal component is simply 40 newtons. The X component of the tension is simply Ft. Step 4 is to apply the second law. The second law is F equals ma, as you know, but we're going to label this m with A and this A with A. This means the mass of A times the acceleration of A. And we're also going to go ahead and label the forces with X because we're looking in the horizontal direction for this. So the net horizontal force, well, it's the force of our pull minus the force of the tension. So they're going in different directions. And this is equal to ma. And the last step says to solve, but we can't solve yet because we need to look at box B. Let's go and do that. Let's shove this to the side and let's look at box B. We're going to draw the diagram in the same way, as a simple square. Again, the forces acting on it, we got gravity, we got the normal force, and we have this, which is the tension of the rope here. We call Ft. That's it for box B. There's not much going on. And we're going to go through the same labeling process. We're going to say M of B and the normal force of B. Now, we don't have to resolve any vectors. we already know the horizontal component is simply Ft. When we apply the second law, we get F equals ma. So the total forces is Ft, so the tension of the string, equals ma. So now we're ready to solve, but this gets a little bit tricky. So here's a detail. Ft is equal to Ft. The tension on both sides is equal because remember, we're assuming that the chord mass is 0. So we're looking for the horizontal force throughout this system. That means we can add the horizontal force from A, which is Fp minus Ft, and we can add the horizontal force from B, which is Ft. Now these two cancel out. So that means we're just left with Fp. Fp is equal to the mass of A times the acceleration of A, plus the same thing for B. So mb, ab. Now since these are connected and the chord is tight, that means the acceleration of these boxes should be the same. The acceleration is equal across this chain of ice cream tubs. That means we can go ahead and factor out A. And we get A of mass of A plus mass of B. And that's our Fp. There we go. We just have to plug in our things and solve for acceleration. If you want to go ahead and do that yourself, you can pause the video and try. But I'm going to do it here. So Fp is equal to A. And the mass of A is 5 kilos. The mass of B is 6 kilos. Divide by this thing, you get A equals Fp, which is 40 newtons, over 11 kilos. And this comes out to 3.64 meters per second squared. That means when you tug on this rope at the end of this two ice cream tubs, it accelerates at this speed. Quick note, by the way, Fp, our pulling force here, only acts on box A. It doesn't affect box B. Box B is moving because of the chord tension that comes from us pulling on box A. Here's our next example, and it involves pulleys. So I'm going to draw a diagram, and that will be our problem. Okay, here's our pulley. We have a bucket of water on each side of the pulley. This is our sketch, by the way. And with this pulley, this second box is 50 kilos, and this first box is 60 kilos. We're going to call this box A and this box B. How do we find the acceleration of these buckets of water? Again here, I went and shrunk down our diagram so that we can focus. We're going to take the same approach as always. We're going to draw a free body diagram for both objects. Let's start with water bucket A. Now water bucket A, we know is 60 kilos, and there's two forces acting on it. We have the tension of this part of the string here, and we also have gravity, which is the mass of A multiplied by G. Let's put this aside and draw our diagram for B. B is the exact same thing. So B, 50 kilos. And it's the same thing, except we're going to call this mass of B times G. And this is still the same force because, remember, we're assuming chord mass is negligible. There we go. There's our two free body diagrams right here. Before we start solving the problem, let's decide our reference frame and coordinate system. Let's say that going down is negative y and going up is plus y. Now A is heavier, so its acceleration will be downwards. And as A goes downwards, the pulley will pull B upwards. We don't have to do any vector component stuff because it's very simple, up and down. Let's go and apply the second law one by one. We'll start with water bucket A. Now you might be rushing into applying the second law. I know, so exciting, right? But before we start, let's find the weight of these two water buckets because that's just going to be useful later on. Multiply the mass and gravity put it into a calculator, you get 588 newtons for A and 490 newtons for B. So the net force for A. I'll let you do this one if you want to. Go ahead and pause the video. Now let's do it together. So the net force is acting on it is the force of the tension pulling it up minus the force of gravity pulling it down. This is equal to negative MA. Because remember, A is going down. Now how about B? Let's do the exact same thing. So MBA. The net force is the net force of this pulling it up, take away gravity pulling it down. That's equal to MBA. This is positive because B is going up. So as you can see, we have found our two equations. Great, so we've done the second law part. Now it's time to solve. Solving is usually the trickiest part because it's just math. Physics isn't really hard. The hard part is math. That's what usually messes you up. So let's go through this slowly. We have two equations. So let's label this as equation 1 and this as equation 2. Let's subtract equation 2 from equation 1. And if you're a little lost, like why are we doing this? How do you know you should do this? This comes with time as you solve more and more physics problems. Your intuition gets better and it's like a muscle in your brain. The more you solve physics problems, the better you get at solving physics problems. If you want specially designed, very specific, precise resources, go check the description. Perfect, we're ready to subtract these equations now. So these two take away, they cancel out. Subtract these, you get negative MBG plus MAG. Subtract these, MBA plus MAA. This looks pretty weird, but it's all part of the process and you have to trust it. We are combining two equations for these two free body diagrams into one equation, which describes the motion of the entire system. And then we apply the second law and find acceleration. That's kind of the big picture. Let's keep solving. We're going to do some factoring. So G factors out. And here, acceleration factors out. Divide both sides by this guy. You get A equals GMA minus MB divided by MB plus MA. So take a second to see what's unknown. A, which is acceleration, is actually the only unknown. If you go and plug in everything, so gravity, the mass of A, 60 kilos, 50 kilos, all that, then you find out that acceleration is roughly 0.89 meters per second squared. So for A, it will be doing that downwards, and for B, it's accelerating at that speed upwards. Let's go one step further and try to find the tension in the cables. Now the tension in the cables is the force we called Ft earlier. And it's very simple. We actually wrote two equations that we can use. So if you've been writing notes, then look back and you'll see this equation, which is Ft minus MAG equals negative MA times A. This is from the very start. It's from our equation that we created from our free body diagram. Go ahead and solve for Ft, plug in your values. So that would be Ft times 60 kilos, 9.8, minus 60 kilos times 0.89, which is our acceleration. And the force of the tension is 534.6 newtons. Here's a fun little fact. We know this is true. We know this is the right answer because the weight of box A was 588 newtons and the weight of box B was 490 newtons. The tension of this cable is between these two weights. This next example is my favorite from today's video. The context of the problem. You're testing a drone. And we'll just symbolize this drone with a circle, very easy. And via a thin string, you suspend a tiny camera so that you can record things. The weight of the camera is equal to 0.5 kilos, and the length of this string is equal to 0.3 meters. The drone itself accelerates forward at 2 meters per second squared. So as you might expect, when you accelerate the drone, the camera and the string is going to swing back. It's going to lag behind a bit because of inertia. So what angle does it swing back? That's what we're looking for. This problem sounds a little tough, but we can rely on our problem solving guideline and we will be okay. So keep in mind what we're looking for. We're looking for the angle. Let's start with drawing our free body diagram. This is our drone. This is the string. That's the camera. Originally, it starts off like that. And this inside angle here is what we're looking for. Let's draw the forces acting on our camera. So the most obvious force is gravity, which by the way, always goes straight down. Gravity is always straight down. The only other force acting on the camera is the force of tension coming from this string. The coordinate system we'll use is, as always, just X going this way, Y going this way. There, that's our free body diagram. Step 3. Break down the vectors. So that means we're looking for the Y component of the tension and the X component of the tension. Gravity doesn't have an X component, it's going straight down. As you know, Ft would be equal to Ft cosine. So that's our X component. Let's go ahead and apply the second law to this. So Ft cosine equals Ma. Now let's do the Y component, which is Fty equals Ft sine. Here's where things get interesting. The upwards acceleration of this camera does not exist. Right, there's no actual upwards acceleration. You might think, wait, what? There is. The camera moves upwards, which it does, but there's no vertical force acting on it that makes it does that. It's simply freely hanging, and the string with the camera happens to get swung back as the drone accelerates. There's no net Y force acting on the camera. So when we apply Newton's second law to this Y component, get the net forces, so Fty minus mg equals 0. Okay, that's perfect. We have found our two components. Now it's time to solve. So we're solving for this angle, and we have this Y component and this X component. So here it's simple. We just have to use the vector direction formula, which is this: the inverse tan function of the Y component over the X component. Now we missed something with the Y component. Let's add mg to both sides so that we can get this on its own. Just Ft sine equals mg. Now plug it in. So tan of Ft sine divided by Ft cosine. From here we can substitute Ma for cosine and mg for sine, which would give us and it comes out to be roughly 11.53 degrees. So when your drone flies forward and accelerates, then your camera will swing back this far, 11 degrees. Now let me ask you a bit more of a conceptual question. So let's say your drone is done accelerating and it starts to travel at a constant speed. What happens to the camera? So the camera will actually just hang straight down because there's no horizontal forces acting on it. By the way, something that really helps me is having all the formulas you ever need in one place. And I make these cheat sheets for myself, and if you want your own, it's in the description for free. So go sign up.